Thanks, Tracy. Well, good evening, everyone. Some of you are gluttons for punishment because I think at least two of you have heard me do this talk or versions of it before. And just to follow on a little bit about my background, I've actually been retired. It'll be 10 years this year, but we're still, the MIRI team and the James Webb team, we are still in touch with people. I spent the last 10 years of my career on JWST as Tracy said, the project manager for what was called the European Consortium. I won't go into all the details of that at this point, but basically Gillian Wright, Professor Gillian Wright at the Astronomy Technology Centre at Edinburgh was the principal investigator or the lead scientist for the European side of MIRI. MIRI was a joint American-European venture, and I was effectively Gillian's project manager. And the space company that is now called Airbus, at that time it was called Astrium, essentially loaned a group of us out to Gillian as the, if you like, the space experts. So we provided the overall system engineering and project management for MIRI, the mid-infrared instrument. So what I'm going to do is tell you a little bit about the background, very quick summary, and then we'll look at some of the pictures. I strongly suspect some of you on this call are much more into the astronomy side than I am, so I apologise if I get any of the details wrong. So let's start with one of the first images that were released not quite a year ago now. And if I normally say to people, if you don't like numbers or techie stuff, just regard this as a work of art. And I think this is just a beautiful picture. This is a MIRI picture, the mid-infrared image of 5 galaxies, 4 of which are interacting. And it is just a lovely picture. So if you don't like anything else, enjoy the images. But of course, everybody thinks JWST stands for the James Webb Space Telescope. But the first images and data coming back to Earth have been so stunning that the astronomers are already renaming it the Just Wonderful Space Telescope, which is a rather nice accolade to have, I think. And again, if we just look at some of these pictures that have boggled people, this is a relatively recent one. This is a protostar reckoned to be about 100,000 years old. And in the middle of the image, you can probably make out a little white disk with a band across it. And what we're looking at there is a protoplanetary disk edge on, but yeah, by chance alignment around this protostar, you have the disk where the planets would form just like our solar system, and we're looking edge on. And what you're seeing is the light from the star energizing sort of dust gas clouds around, and you've got this just incredible picture. So there we are, the birth of a new solar system. 100,000 years, of course, in astronomical terms is just nothing. But key point is that JWST is an infrared space telescope. It only collects infrared light. If you're familiar with Hubble, you'll be aware that Hubble is primarily an optical light telescope with some ultraviolet and a tiny bit of infrared, only into the very near infrared. And because James Webb only collects infrared light, one of the questions we often asked is, well, how can we see pictures? Because our eyes can't see in the infrared. And I think probably most people here, it'll be a statement of the blindingly obvious, but all the James Webb images are in false color. The information in the infrared is translated into the visible light that our eyes can detect. And I think there's an audio analogy of people say, well, how does that work? You say, well, look, I'm sure everybody's heard the sound of bats flying around with their ultrasound, making clicks and getting echolocation. And you can translate the frequency into an audio frequency that we can hear. So it's that same sort of thing. In fact, many of the Hubble telescope pictures are also in false color. I think that's not fully appreciated. Colors can be picked to highlight certain features. They can provide contrast. They can be very helpful scientifically. And you can process the same image in multiple ways. There is no right or wrong way to do this. And some images are processed just to produce a beautiful or stunning picture. There is something called the Hubble palette, which is a kind of a way of translating images, but there are no hard and fast rules. And so, again, apologies if this is a bit basic for most of the people here, but I like the analogy of what we do and do not see. And imagine the electromagnetic spectrum, all radiation was a giant picture window. If we try and put it to scale, it'd have to be much wider than your computer screen. But what we see is a very narrow band. We're looking at visible light. And this, again, if you wanted to scale it, it would be an incredibly thin bit of light coming through. But if you like, we're looking out at the universe, we can only see invisible light. If we have the ability to look into the infrared, on this picture, I'm taking wavelength effectively left to right. So the longest, the shortest wavelengths are on the left and the longest on the right. So visible light's about 0.4 to 0.7 microns in wavelength. And hidden behind the screen, which is equivalent to us not being able to see, is the infrared. If you keep going that way, you'll get to radar and radio and all the low frequency stuff. If you go to the left, we are into the ultraviolet. Again, our eyes can't detect that, but some animals can. And if we keep going up from the ultraviolet, we'll eventually get to X-rays and gamma rays. And this is just to sort of illustrate the really narrow band our eyes let us see. And so using telescopes that can look further into the entire electromagnetic spectrum obviously gives us a lot more information. So what is a space telescope? Well, actually, it's not just a telescope in space. The telescope collects light. On the ground, we look into an eyepiece to see an image, or we use a camera to capture it. But to be of any scientific use, a space telescope has got to carry its own cameras and other instruments, because it's not an option to carry astronomers. I mean, apart from the fact that they would primarily contaminate the optics, which we don't want, they'd freeze, starve, be radiation damaged, and generally be a nuisance. The telescope's also got to be launched, pointed, powered, controlled, and communicated with both ways throughout its lifetime. Every photon of light the telescope collects has got to be turned into an electronic signal. That's got to be digitized, transmitted to Earth by a radio link. Then that data can be reassembled into images or spectra for analysis. So a space telescope is also a spacecraft and a system. It's a very complicated object. Engineers like hierarchies and diagrams, and the entire JWST system can be thought of as in 3 segments. Now, we do tend to be a bit loose with the terminology, because sometimes we'll say JWST, sometimes we'll say the observatory, sometimes we'll say spacecraft. And it's because the people working on it, obviously, you know which bit you're talking about. So sometimes if I use a term, bear with me, I'm generally referring to what is known as the observatory, the bit flying in space. To get that up there, we need a launcher, or we needed a launcher. So there's going to be the launch vehicle, something to fit the payload, i.e. JWST, onto, and all the launch site services. The observatory itself is 3 major elements: the optical telescope element, the integrated science instrument module, or ISIM as it's known in the business, and then the spacecraft element, which you can think of as a box that we call the spacecraft bus, which is all the standard stuff on every spacecraft. And in this case, this enormous sun shield. But to be of any use, you've got to have a ground segment to talk to it and collect data. And so there's a science and operations center, which is in fact the Space Telescope Science Institute in Baltimore, not that far from the Goddard Space Flight Center at Washington, D.C., where the whole project was run from. And STSCI, as it's called, is tied into the Deep Space Network, both the ESA and the NASA ones. And there's a whole raft of protocols and how you command and deal with telemetry for that sort of thing, but we won't go into that now. So here's a classic artist picture of the observatory, which is the sort of picture that sends engineers mad, because they've nicely got the sun reflecting off the main mirror, which of course, if that was real, would have completely destroyed the alignment and overheated all the critical things. But that's the difference between the engineering world and the artistic world. So we mentioned the 3 observatory elements. So to pick those up again, starting at the top, we've got the telescope itself. That gathers and directs light onto the instruments. We have an instrument suite that takes that light, takes images and analyzes it and turns it into data. And the spacecraft bus is typically a box. It has solar array attached. It provides the observatory with the power, the pointing, the propulsion, critically the thermal control. That's absolutely a vital part of the design, and the data handling and communications with Earth. Looking at these more diagrammatically, and the colors here don't mean anything at all. This is a sort of stripped down version. On the left, you can see the primary, secondary and tertiary mirrors of the main telescope. The sun shield, which is literally the size of a tennis court, albeit a bit squashed. And at the right-hand side, the ISIM, the instrument module, is mounted behind the main mirror. And the light comes off the secondary through the hole in the center of the main mirror into the instruments. Looking at the back plane that supports the mirrors, there's sort of triangular features schematically shown there. Those are the actuators, and each of the 18 primary mirror segments can be adjusted with 7 degrees of freedom. So you can move it in, out, up, down, side to side. You can rotate about each of those 3 axes, and we can actually flex very slightly each of those mirror segments to change the curvature. And all that was built in as degrees of freedom to make sure we could align everything and hopefully avoid any Hubble type problems. There is no way anybody can go and service JWST. The spacecraft bus is the box at the bottom, and there's a red tube connecting them. That is actually a telescoping tube. So the telescope telescopes off the spacecraft bus after launch to give it some clearance so the sun shield can open out. And that's to reduce the thermal flow from the hot side to the cold side. The bus is on the hot side. For those with a particular astronomical bent, it's a 3-mirror anastigmatic design. It gets a wide field of view, and basically it does away with the 3 classic aberrations or coma you get with a telescope. It's an F20 telescope, which means the effective focal length is over 131 meters. It is basically a Cassegrain design in simple terms. And the optical resolution is about 0.1 arc seconds at 2 micron wavelength. And we have to specify the resolution at a wavelength because it does change it. And that is incredible. What that means is you, in theory, could resolve a 1p coin at a distance of 40 kilometers or 25 miles. And I always have to hesitate to say this because this was a NASA slide, and they claim that thermally they could detect a B at the distance of the moon. And I've lost track of the number of times at the end of a talk people have said, so how many Bs are on the moon? But I'm sure none of you will be asking that question. So let's look at a few pictures of real hardware. And this was at the Goddard Space Flight Center. This is the clean room where Hubble was assembled. And there is the primary and secondary mirror with a person in a white bunny suit at the bottom for a bit of scale. For launch, the secondary folds up over the top. And here is the instrument suite. Nobody's too interested in instruments apart from the scientists and the astronomers who want the data. But it gives you some idea again of the scale. 4 main instruments. I'm not going to go into all the details of those right now, but it's on a very large carbon fiber tube structure, which in itself was a tremendous piece of engineering. That was done by Goddard. And there is the 5-layer flight sun shield, the thing that actually got launched. Again, you've got people to give you some idea of scale. It is gigantic. And here was the integrated observatory with a folded telescope. And this is where the sun shield, it folds onto 2 pallets fore and aft. And then those pallets fold up and we end up with an integrated observatory. It's at over 11 meters tall, and that is the way it is stacked to go on top of the rocket. This was the 23rd of December 2021, being moved to the launch pad in French Guiana. Part of the European contribution was the Ariane 5 launch, which was a very significant part of the project. Finally, at the launch pad, I think that's a Christmas Eve photograph. And on the 25th of December, Christmas Day, I think as Tracy was saying, I think I spent 8 hours watching NASA TV that day. We launched. I don't know how long the NASA commentator spent working out the line, lift off from a tropical rainforest to the edge of time itself, but I thought it was pretty good. And there was Christmas. And this was our final sight of James Webb as it headed away after it was released from the upper stage of the rocket. There was a little camera in the top taking an image. There was actually a very good video. You can even see the solar array deploy on that. And of course, it's all wrapped in thermal blanket, and it looks like a Christmas present carefully wrapped up with, of course, the Earth in the background. It then took basically 2 weeks to unfold, which was probably the most nail-biting part of everything. I'm going to show a very short video, highly speeded up, of the main events, just to remind you if you missed it. And it's got its own commentary on there. I'll just let you have a look at that. So I'm hoping you can still all hear me okay. You're probably all aware that the spacecraft is not in orbit around the Earth. It's gone to this point called L2, the second Lagrange point. An infrared telescope has got to be incredibly cold to detect the very faint infrared light from the very distant stars. And we were trying to get to the very first stars that lit up after the Big Bang. So we need to be very cold to get that sensitivity. We're talking minus 233 C or 40 Kelvin in engineering units. Kelvin being the absolute scale of temperature starting at absolute zero. Deep space itself is at a temperature of about minus 270 C or 3 Kelvin, and it provides a natural deep freeze. And it was felt when the design started that we could use this deep freeze to cool the telescope and the instruments down to the critical operating temperatures we wanted, i.e. about 40 degrees above absolute zero. But the telescope and instruments have got to be connected to the spacecraft bus. There's got to be motors and detectors and all sorts of things that are going to generate heat. So there's a very careful heat balance. And we also have got to avoid heat radiation from stars and planets, in particular our star, the sun, and our moon. Now, L2, I'm sorry for the mouthful here, but it's a quasi-gravitationally stable location. It is actually a point orbiting the sun. It's about 4 times further from the Earth than the moon is in the direction away from the sun. I'll show a diagram in a moment to make it a bit clearer. But if you're at L2, the key thing is you keep the distance between the Earth and the spacecraft pretty constant. You keep the sun, Earth, and moon in the same direction, and therefore a giant sun shield will block their thermal radiation. Now, you don't have to be exactly at L2 to benefit from the properties. If you like, L2 is a mathematical point, but there's a huge volume of space you can operate in. Several spacecraft are there already, more are planned, but there's no real risk of collision. We're talking about enormous volume of space. So here is a definitely not to scale diagram. The sun is the white blob just left of center. The 5 Lagrange points are marked around there with the Earth and the moon. And very definitely not to scale. This shows you what's going on. So as the Earth tracks around the sun, James Webb tracks around the sun at the same rate. Now, in theory, to be in a stable orbit, it will be orbiting slower than the Earth does and gradually slip behind. But because of these properties at L2 of the mathematics of the way the gravitational forces work, you can leave a spacecraft there and it will track round at the same rate. It's not totally free. You do have to do some station keeping every few days, but it's a very small amount of fuel you need to fire a little rocket engine just to keep it in the right place. So that's the advantage of L2. Moving on to infrared space telescopes more generally, this is 3 generations of infrared images of the same bit of sky, starting from the left, and you can see as the technology improved how we are seeing so much more detail than was possible before. And this was the first engineering image released almost a year ago. These are actually the fields of view of the 4 instruments, and some of those have been expanded out to show you what the detectors actually pick up. The key thing about this image is people realized right from this point that it was going to work. It was going to work spectacularly well. There were 4 key science goals when we started, but already people are talking about using this for so many more things. The one that really got the job going was top left, which is first light and reionization, the epoch of reionization. And that's really where we're trying to get back to those first stars and galaxies. Hubble physically cannot get and see those early stars and galaxies because the light has been traveling for so long, the universe has expanded in that time, and the peak energies from that first light has been stretched out of the optical into the infrared. And Hubble cannot see far enough into the red to properly see these first stars and galaxies. It can get a long way back, but it can't get as far back as James Webb. But also things that drove the design of this were how do galaxies assemble? There's a lot of unknown about that. And when did the first galaxies start assembling? With that goes the birth of stars and protoplanetary systems. And of course, the follow-on question is, about the planetary system themselves and the origin of life. And interestingly, when the job started, it was a pure near-infrared telescope. It was only after the job had been running for a while that a bunch of European and American scientists persuaded NASA that you had to have the ability to look in the mid-infrared, i.e., for those interested in numbers, about 5 to 30 micron wavelengths. The near-infrared is only going up to about 5 microns. And without that ability, a lot of this information could not be properly put in context. And in fact, it has now, MIRI, the mid-infrared instrument, has become the only instrument that is absolutely fundamental to all 4 science goals. Such is the way things evolve. So that's all I'm going to say about the background and the getting the thing into orbit. Let's look at some of the images. And this was one of the first ones that was released, a deep field. And the staggering thing is, for those of you that are familiar with the Hubble deep field and the ultra deep field, etc., and there's a north and south version, the original deep field was 10 days just staring at a blank bit of sky. And of course, the result was staggering, just galaxies everywhere. I think the ultra deep field was 2 weeks non-stop staring. James Webb took this image in 11.5 hours. And this is just the beginning of its capabilities. So what he's going to reveal is incredible. But one of the things that came out of this was you can probably make out the rings and arcs look a bit distorted. And that is because it's imaging a distant galaxy, that a galaxy or group of galaxies in between JWST and this very distant galaxy are acting as a gravitational lens. And what we are seeing is Einstein rings. And that is a pretty remarkable image. But there's a couple of things we can close in on. You can see more of the arcs there, and you can use that, interpret that data and get information about how far away that galaxy. It's one galaxy with lots of separate images appearing in arcs. But also, we're just picking up spiral galaxies. Obviously, we think our Milky Way is a little bit like that. And let's go back to Stefan's quintet where I started. Now, this is a combined near and mid-infrared image. So you're getting different information about the dust, the gas, the new stars being born. And this is going back to just the mid-infrared image. And the bright spot at the top, or just right of top, I believe is thought to be a 24 million solar mass supermassive black hole. 4 of the galaxies are interacting, said one is a line of sight effect. But already from the very beginning of these images, there was vast amounts of information coming and exciting the astronomers. You probably remember this one as well. We're looking at starbirth clouds of gas and dust. This is about 7,600 light years away in the Carina Nebula. They make just amazing pictures anyway. And that's where stars are born. This is where stars die. Again, this is one of the first set of images released. On the left is the near infrared picture. And you're looking at effectively the death of a moderate mass star blowing off the dust and gas. If we look just in the mid-infrared, we can actually resolve that the parent star was actually a double star, one of which has gone into death throes. But also, if you look to the left of the image, you might see a little line. And this was zoomed in on, and it's a pure chance effect that between all the dust being blasted out, you're looking at another galaxy edge on. Just happened to get it photobombed the image. And some of the later images looking at galaxies, this is M74, about 32 million light years away. And this is where we're picking up the birth of new stars looking through the dust that the optical telescopes won't get. The Cartwheel Ring Galaxy, 500 million light years away, again, a combined image. I believe this is thought to be an interaction of a couple of galaxies, and it is quite an incredible sight. But of course, it's not just the image, it's the details and the information that can be drawn out of this that is providing so much information for the astronomical community. And we've even done an exoplanet image. This is a young gas giant, probably several times the mass of Jupiter. And what we've done here is using both the near infrared and the mid infrared. NearCam is a near infrared camera. It is possible to effectively block out the light of the parent star, and the white star symbol represents where the parent would be. And what you're looking at is images of a planet. Now, this is a very big planet, of course, several times the mass of Jupiter, but nevertheless, we're right at the beginning of starting to look for exoplanets. The two pictures on the left, what look like the shadow bands around it, they are artifacts of the image. But this is pretty exciting stuff. We're getting images of planets, exoplanets. And also, they turn it onto Mars. Now, there is no way JWST can ever be pointed inwards at all times. The sun and the moon and the earth have got to be kept behind the sun shield away from the telescope. So you can never point it across the solar system at a target of opportunity. You have to wait till the orbit brings you round far enough to get there. But one of the big challenges was whether we could look at Mars. Obviously, it's the closest of the outer planets from Earth. So it's very bright and it's moving very fast in comparison with the sorts of things JWST was really intended to look at. Nevertheless, and special precautions had to be taken not to saturate the detectors. It's picking up information from Mars, and this just shows how good the tracking and the control of the spacecraft is. But also, some of these later images picked up Neptune, 7 of its 14 moons, and the dust rings. Triton is on this image, those are the diffraction spikes you expect with a sort of bright image. But if we focus in down to Neptune, a big and infrared image, of course, we're getting a different view of the planet, but it is picking up the dust rings beautifully. And here's a bit of an oddball. This surprised people to start with. It's a binary Wolf-Rayet star. And I think every 8 years, the two stars, their orbits bring them close enough and it blasts a dust shell off one of the stars. And what we actually saw was, I think there's 17 dust shells coming out every 8 years, you can see there. And that was really an incredible picture. Again, the diffraction spikes, the bright star at the middle, but more information than people thought would be possible to get. And Hubble and Webb are actually doing complementary science. It was always hoped that Hubble would last until Webb got there. Of course, Webb got delayed significantly, but Hubble has kept going. And again, this is a spiral galaxy, and we're looking on the left with the Hubble in the ultraviolet and the visible and the mid-infrared looking through the dust at the structure and the new stars behind there. And by putting all these different wavelengths together and extracting the information, you get a lot more than any one telescope or detector system can give you. But Hubble and Webb also did simultaneous observations, and you probably remember the double asteroid redirection test, the DART mission that was done some months ago. And this was the first time we'd actually had Hubble and Webb looking at the same thing at the same time. And that's really valuable information for sort of cross-calibration and so on. I think many of you will be familiar with the famous Pillars of Creation picture on the left, the Hubble picture. But taking the same image, and this is about 6,500 light years away, in the near infrared, this is where you can actually begin to understand how much an infrared telescope peers through the dust and starts to reveal details of what's going on in those dense dust clouds. But we can also actually tune what we're looking at to actually look at the dust. And this is the same image taken by the mid-infrared instrument, focusing really on the gas and dust. I think this actually looks quite sinister. But again, this is showing the sorts of things we can do and the way the instruments can be used for extracting different types of information. This is a galaxy merger. This is possibly forming a supermassive black hole about, supermassive black hole about 270 million light years away. And we mustn't forget, for most of the astronomers, the key thing is the spectral data. So this is an exoplanet atmosphere. It's never been seen before. In other words, it's a molecular and chemical portrait of the skies of a distant world. I'm not going to dwell on this because we could talk for hours about the spectrometry side of this. But the data is coming in. And already the earliest galaxy to date has been found, and it's caused no end of problems. It's only about 350 million years old, 350 million years after the Big Bang, if you like. It is puzzlingly bright. And the problem is that means the first stars in it probably formed only 100 million years after the Big Bang. I think when when JWST began as a project, it was felt the first stars were maybe 400 billion years after the Big Bang. Already the books are going to have to be rewritten, theories are going to have to be reworked. But what we're looking at there is a part of a deep field, and the little box on the left with a 1 and on the right the 2. If you zoom in, what you're seeing are the little red dots are these distant galaxies. And so these very early galaxies are already a bit of a puzzle. And then this January, we got the first exoplanet transit light curve. And this is a planet that's pretty well the size of the Earth. And the aim there is to characterize the atmosphere. And this is all work in progress. But this, again, it's show you the kind of data collection and the fact we can discriminate. If you look at the left-hand scale, we're looking at very small differences in brightness, but look how close the data points are together. You know, it's obvious that is not just an anomaly. And this is a spiral galaxy amongst thousands, but this is about 1 billion light years away, or thought to be, and virtually everything in that image is a galaxy, and so much of it is redshifted. We're also looking at star formation in what you might call a nearby galaxy, only 46 million light years away. But again, what we're seeing is detail never been revealed before. So how big an advance is Webb? It is looking into unexplored territory at light that has never been detected by humans before. And I think that's a really significant statement. I'd like to say it again. This is light that humans have never been able to detect. It's light from the cosmic dawn, when the universe became transparent, after the cosmic microwave background could travel. We're talking about 13.5 billion years ago. We are literally seeing our universe in a whole new light. What's more, the astronomers will say that it represents a pinnacle in mid-infrared astronomy in particular, because to put together the resources that could significantly surpass the capabilities of JWST, it is basically unimaginable for the foreseeable future. And I don't think anybody's going to want to spend the kind of money that Webb ended up costing NASA in the near term. And the observations that JWST will make will serve astronomy for many decades to come. Any postdocs or even graduates right now, they could well be working on this data right through their careers, and it should make a unique contribution to human knowledge. And it's been my privilege to work on and contribute in some way to this monumental project. I am really grateful I had the chance. So how can I sum up the science operations to date? Jane Rigby, who is the operations project scientist at Goddard, she said, well, it's actually a couple of months ago now, that this has been a gift that has taken months to unwrap, and the result was almost across the board. The observatory is more powerful than our pre-launch expectations. This simply reflects engineers' conservatism and wanting to be pessimistic. The images are sharper, the pointing and guiding are more stable with darker skies, darker backgrounds, and greater and better sensitivity. And there is a flood of new discoveries pouring in, just as we hoped, especially on the first light, the early stars and galaxies, which was the main aim. But the real excitement to my mind is that the science is only just beginning. There are 20 years worth of fuel on the observatory. That is down to the fantastic performance of the Ariane 5 rocket. It injected it so accurately, they saved a lot of fuel they thought they might need to get on station. And there's a whole discussion about what kills spacecraft in the end, but fuel is usually one of the key ones. But we've got 20 years of fuel on board. So watch this space. Thank you for listening. I hope that was entertaining.